Anyways, what I wanted to say is that the dot product is a measure of how aligned two vectors are.
Exactly.
So if the vectors are pointing directly like in the same direction, then the dot product is going to be at a maximum. And if we're only talking about unit vectors, then the dot product is going to be 1. And if the vectors are pointing opposite to each other, then the dot product is going to be at a minimum, or unit vectors is going to be -1. There's kind of this understanding of what aligned means, and it's not like as if the two vectors are like completely pointing in the opposite direction. That's not really like what we're really interested in. I think the most important thing about a dot product is that when the two vectors are orthogonal to each other, you get a dot product of 0. And this is the exact moment at which, if you were to, like, to me it seems a little bit magical, but if you have two orthogonal vectors, they could be, 100 dimensional vectors.
Doesn't matter.
You have no idea what they look like. But if you multiply each component and add them together, you would get 0 magically. And you
By the
would
way,
know that
multiplying component and adding together is what is the process of the dot product, right? So basically,
Yeah.
I don't know if we've been through that, but like that's an essence. Like the cosine theta is one version if we know the lengths of the vectors, but a lot of the times,
angle.
yeah, and the angle. A lot of the times we don't know that, right? They can just be like all frolicked around all over the Cartesian plane. So we don't necessarily know their magnitude or the angle between them, but we might know their coordinates. Now, if we know their coordinates, that's what you were talking about right there.
I mean, what you said kind of didn't make any sense.
Yeah, okay, it can't be fraud. It has to be
coordinates,
from the
you can
origin.
find
Yeah,
the
you're
length.
right. You're right. No, you're right. You're right.
No,
You're
but
totally right.
if you know the coordinates, you can find the length, right? Like the only thing that you need is the angle, which is usually something that you can't just pull out your, what's it called? Like the angle finder. You know what I mean? Anyway.
The tan thing? Yeah, no. I know. So moving on from the dot product, we've already talked about the scalar product. Now let's talk about the kind of intuitive next step, the vector product, also known as the cross product. So the cross product is a very interesting tactic, like a multiplication tactic. Again, these are just basically vector multiplications, right? One is a scalar multiplication, which is the dot, and one is a vector, which is this one. So the cross product, in essence, the formula, again, not that it matters, but instead of cosine, we use sine theta. But again, that might, not really make sense to anybody, but let's just explain the cross product as what the cross product really means. So when we're talking about the cross product, we're basically asking for, hey, we have these two vectors. What I want is an orthogonal vector to both of these vectors. So the most common example, like if I have 1, 0 and 0, 1, which is like your unit vector in the x direction, unit vector in the y direction, right? You take the cross product, you get the unit vector in the z direction. So typically, if we just had the xy plane and we took the cross product, we wouldn't be able to do it. It would literally not work because we need a vector orthogonal to both of them for the cross product to work. So in a two-dimensional plane, in a two-dimensional coordinate system, the cross product simply is not a thing, right? So that's an interesting thing with the cross product. But what is the value? What does it represent? And I don't actually know why. Maybe you do. Maybe we can talk about this. But what the value of the cross product represents, and this is interesting, is the area. Now, how do I explain this without visual aid? Like the area of the parallelogram subtended by the vectors. So let me repeat that. If you put the vectors tail to tail, so both the vectors are kind of coming out from there, and if you just kind of draw a parallelogram, so you copy the vectors twice, basically. So you draw one here and again, for the video watchers, it might be easier. I have no idea how the audio guys are listening to this.
Yeah, I think the details don't really
matter.
matter.
Detailed, I think I got a little too deep into it, but like just the essence of the cross product is important.
But I do actually have some information on this. So
Okay. Let's hear it.
the scalar product and the vector products are essentially opposite. Depends on what your definition of opposite is. But the cross product is a measure of how unaligned the vectors are. So if the vectors are completely aligned, and when I say aligned, I mean like part of the same line. So this means that if your vectors are pointing in the same direction, they're on the same line, the cross product is going to have a value or a vector of length 0. And if your vectors are completely unaligned and they're 180 degrees pointing the opposite direction,
No, 90.
Your cross product is also going to have I meant 180 degrees. Your cross product is going to have a value of 0 also.
0.
You're going to have
yes.
you're going to have a max value when you have a right angle. And if you listen to what Ray said, if you actually draw the parallelogram, you actually get a square. And so if you have but if you have two different side lengths, it actually shows you that to get the maximum amount of area with these side lengths, they have to be perfectly orthogonal. And one thing that's really useful about the cross product is that you can actually define an entire plane with one vector. And this is very beautiful, because here's the thing. Let's say we're in 3 dimensions and you have a plane. Okay? One thing that you can, just by looking at the plane, is that if you were to draw an orthogonal vector to the plane, that there's 2 options, right? You can either, and we're talking about unit vectors here, because if we were to talk about like any possible vector, then there would be an infinite amount of vectors. But if you were to talk about orthogonal unit vectors to the plane, there are only 2. There's one pointing in one direction and another one that's pointing directly in the other direction. And so if we kind of think about those 2 vectors as the same vector, because essentially they're just the same but with a minus sign, right? We can say that there's just one single orthogonal vector, okay? And actually, if you were to take any 2 directional vectors in the plane, you take the cross product of those 2 vectors, you are going to get a vector that's orthogonal to the plane automatically, because that's how the cross product is defined. And then when you normalize that vector, you get the unique unit vector to that plane. And so one thing that's awesome about that is that if you take the dot product between that vector and any vector that's a part of the plane, you will get 0. And so here's the beautiful way to define a plane. Okay, so you have your unit vector. Let's say your unit vector is ABC, right? We're in 3 dimensions.
So A comma B comma C. Yeah, exactly.
A comma B comma C. When you take the dot product, you get, the first 2 inputs, or the first 2 variables multiplied together, added with the second, added with the third multiplications, okay? So here's how you define the plane. You just define it as AX plus BY plus CZ equals 0. Because you're essentially saying that...
Well, this is by the way, origin, though, but yeah.
Yeah, this is if the plane is on the origin. But what you're saying here is that, and I forgot to mention that XYZ is just like any vector. And so what you're saying is that when you take the dot product between your normal vector and any vector, it'll be equal to 0. But as I mentioned 2 seconds ago, this unit vector is unique to the plane. And so automatically, if you do get this relationship where the dot product is 0, you have a vector that's in the plane. So there you go.
And that vector that you were talking about is called the normal vector. And that form that you were just talking about, that AX plus BY plus ZZ, is called a normal form of a plane.